So just some very high-level points I want to make here. Decomposition and search are important principles in machine learning. I could take a data set like this, and one thing that decision tree induction makes clear is, or it makes explicit, is this idea of decomposing that data set. So here I might initially split on whether the value of data was greater than m or less than or equal to m. And I would split the data this way. And then at another branch in the decision tree, the lower branch, I might split again on whether the data is less than n or greater than or equal to n. And so I've taken this data set and I've decomposed it. And in general, there are variations on decision tree induction that will then fit as best it can the data within those subpopulations. So in a variation of decision trees called regression trees, and you read about regression, making a prediction along a continuous attribute or variable. In regression trees, it might decompose the data based on something like this until it gets to subpopulations in which it can provide a good polynomial model or fit to the data. So in the case of two of these subpopulations, there is a good linear fit. In the case of another subpopulation, there's a good second or third order degree fit. And the decision tree is, or the regression tree is actually constructing a piecewise model in this case. So if something falls within this region, you use this linear line to predict it. If something falls within this region, you use that linear line to predict it. If something falls within this region, you use that second or third order polynomial fit to fit it or to predict it. And there are lots of variations here. Just highlighting some in blue. Termination conditions were something we talked about. Very briefly, we talked about regression trees. I and a student once used regression trees. It was a pretty well-cited paper on predicting software development time, where software development time was the continuous dimension. So you had characteristics of a software package. This is an IEEE software engineering, and based on the characteristics of the software spec to be developed, you would make a prediction as to the person months to develop that project. And we compared regression tree learners with neural net learners. And they both did well, okay, in different circumstances. But that's an example of a real world regression problem in which you are making a prediction along a continuous dimension, like development time. Or a million other things. A couple other high-level things I want to talk about are less greedy variance and then ensembles or forests of decision trees. So the greedy approach that we looked at, and which frankly is standard, you could think of in the language of the book, chapter 4 in particular. I put it in quotes because the book talks about hill climbing in the context of constraint problems, and this is not really a classic constraint problem, but the idea of a hill climb is still relevant here. We're starting with an empty decision tree, and each step we're adding an attribute. So I'm not showing the values of the attributes here. I'm just showing V1 is selected as the root here. V2 is selected as the root of the left subtree. V3 is selected as the root of the left subtree. And we take a straight line, essentially. Each addition on each recursive call is fleshing out this tree. This is what is known as hill climbing or gradient descent, if it was a continuous domain. But you can still do decision tree learning in the context of a broader search. It doesn't have to be a hill climb. It doesn't have to be a greedy approach. And what you might do is you might have a more systematic approach for the best decision tree. Every node here in this state space search is a partial decision tree, along with the data that was used to build that tree, etc. And so along this branch, you might investigate all subtrees that, this could be a very large subspace, that are rooted at V5. Here, which was our original example, rooted at V1, rooted at V4. And there'd be some other branches as well. And so you could do decision tree learning using state space search, where each state in the state space was a partial decision tree. And if you were interested in having small trees or accurate trees, the greedy approach in general does pretty good. Because in this particular application, a hill climb, and you could think of the information measure that we're using to do the selection and the termination function that we're using as operators in the state space search, but we're only following one path. You could adapt those operators to do a more systematic search. Would take a lot more time, but you could then be in a position of better answering. Do I have a really small tree or the smallest available tree, if you believe in Occam's razor, and it's a good rule, or the most accurate tree? And you can do a better job of answering with a more systematic search. We'll probably briefly talk on Thursday about how this might be relevant to the project and how you can use supervised learning for that. So some of that might be relevant. The other thing I want to talk about is decision forests or ensembles of classifiers. And it turns out that ensembles of classifiers, there are different kinds of classifiers. We talked about deep learning neural net classifiers, just brief mention. We've gone in depth about decision tree classifiers. But if one classifier is good, what about many classifiers? What about building many classifiers for one prediction task? So you might use them using different techniques. I might build a classifier using decision tree induction for my movie watching behavior, and a neural network classifier for my movie watching behavior, and et cetera, et cetera, et cetera. And I could vote them in the end. That's not the standard way of building classifiers. You don't have multiple representations. But sometimes it is the case that if one classifier is good or good enough, many is even better. And there's lots of variations on building, in this case, decision forests. But this general idea of ensembles of classifiers is a more general concept that you could use even if you use something besides decision tree. Of the many or the several methods used to build decision forests, bagging is the only one I'll talk about now. Now, I've got one set of training data, and I've outlined the greedy decision tree algorithm for you. If I run that greedy decision tree algorithm on a data set once, I will get a tree. What if I run that same decision tree algorithm on the same data a second time? Do I hope I will get the same tree? If it's the same algorithm, I hope so. If I run it a third time, I will get the same tree. So if the forest is all identical trees, that doesn't do me any good. There are different ways to make sure that you get different trees. One would be to throw in a kind of random element, a stochastic element that said, randomly choose, don't always select the best, but randomly choose amongst the top 10 attributes. And that will build different trees, okay? Another way to build different trees is through bagging. And here I embed a greedy decision tree induction into the greedy decision tree algorithm into a loop. And for iterations that equal the desired size of the forest, I build a separate training set for each of those iterations. And the training set for each iteration is created by randomly sampling from the actual training set with replacement. And what that means is I got this training set, it's size n. I select n items with a replacement. And sometimes that I'm going to get duplicate items. So if I've got n items, and I'm drawing something on the board now for those that are watching. These are my 4 items. I randomly sample 4 items with a replacement. On one instance, I might get 1, 1, 1, 1, 3, 4. Notice that 2 does not appear in there. That was 1 sampling with replacement. I sample again with a replacement, and I get 1, 2, 4, 3. In that case, I've gotten all the instances. I've gotten the original. But I sample a 3rd time. 2, 3, 4, 3. In that case, I have not selected 1. Okay? So I do this, and I would do 1 more random sample. In each case, I get slightly different training sets. They are very much like the training set from which I am drawing, but they are different. Every training set is potentially different and probably different, particularly if the sample is very large. Every sample will include some duplicates for the most part, and every sample will omit some instances for the most part. And so I've got these different training sets, and from those different training sets, I build different decision trees, in theory. And that's another way, called bagging, to get that variation in decision trees that you want if you want to take a vote that is meaningful. There is a theory behind bagging if it doesn't sound intuitive, but it works well. It does not work as well as some other less intuitive approaches. The reason I'm talking about bagging is it's one of the more intuitive approaches. The other one, again, is to throw in the stochastic element where you're randomly selecting amongst the best attributes rather than always selecting the best. That will give you different decision trees. Both of those approaches will do pretty well. Just a few more comments on decision trees. To highlight something I talked about at the beginning, decision trees are used to learn disjunctive concepts. And you know, my movie watching behavior is certainly best characterized as disjunctive. If you don't believe in disjunctive concepts, think about your own watching behavior. And you would be hard-pressed, I think, to come up with a simple conjunctive description that indicates what you like. Each path in the decision tree, here in the purple, represents a conjunction of values. So if I want a disjunctive representation for rent it, I look at the conjunctions of all paths that lead to that outcome in the form decision tree. And so along one of these paths, Ebert didn't like it. It's a sci-fi with a big star, rent it. So that's one instance of, that's one conjunction within this disjunctive normal form expression for my watching behavior or whoever's watching behavior. Okay, so decision trees are used to represent disjunctive concepts. You could do the same by following the path with not rented. And this is the representation that you would get. Just look at all the not rented nodes and form the paths from there as and disjoin them, and you would get a disjunctive normal form of not renting it. The important thing is that in the decision tree covers all instances. So if I've got rented and I negate rented, and I apply and I convert this to disjunctive normal form, that is, I simply negate this expression and then convert it to disjunctive normal form, I should get what I got explicitly when I looked at the individual paths for things. And so here I've simply shown that negating the positive case will produce the negative case after converting. Looks like, oh, okay, there I am. The other general property of decision trees that I really like that make them in my mind, a good introduction to machine learning is this notion of recursive decomposition. And the decision tree explicitly encodes the context for its more nuanced decisions. This choice here finds a context for understanding what that subtree looks like. It's not only important for when you build the decision tree, but when you try and understand its effects after the fact. And it looks like I skipped a slide here. Just important, a decision tree can be used to represent a logic program as well. This is the relationship between the decision tree and a logical expression, which I also talked about here, taking this form of the decision tree rules and converting them to a propositional form that was the subject of Chapter 5. And again, you can do this to represent logic programs and a knowledge base of logic rules that you might use in a theorem prover. So if you've got a lot of rules in your knowledge base, you could look them up very quickly, perhaps by organizing them as a decision tree. And perhaps we'll come back to that. We are out of time.